Okay, I think I've done everything that I'm supposed to do.
Peter, you have to open the slideshow, or at least I can't.
Okay, you were 1 second ahead of me. Okay, so hopefully everyone is seeing my screen here. We're going to talk about two topics today. The last of the two really very technical algebraic topics that we have. Very important that you remember factoring and a little bit more about handling fractions, because fractional equations come up all the time in nature. So it's important that we're comfortable that I've shown you many examples of fractional equations here that you can practice with. So as we look at phenomenon of nature and things that I have in store for you for us to study and investigate mathematically, a lot of them are in fractional nature. Okay, so we'll start with the first topic of factoring. Why is factoring important? Well, it has a number of different uses. One, it's used to simplify expressions. Here's an example of the factoring: 4x squared plus 8x. The 4x can be factored out, so that if you had two expressions which things can be factored out, turns out if you can factor out the 4x from both the top and the bottom, they will cancel out, because 4x over 4x is just the number 1. And that would be left with a much simpler expression. So there's one example of how factoring is used. Notice what I've done with the factoring. I'm looking for common factors, pulling them out. So if I were to use the distributive law back in, I would get what I started with. And that's one nice thing about factoring. You can always check whether you factored it correctly. Simply just multiply back through and see if you get back what you started with. It's very easy to check if you've made a mistake by just multiplying back through. Another important use of factoring is it's used to solve some quadratic equations, and quadratic equations will become very important for us, because the equations of the second degree when we turn them into geometry, are the conic sections. Those are the parabolas, the ellipses, and the hyperbolas. And that is, among other things, the trajectories of objects moving under gravity. So quadratic equations is a very important topic for us, and it's good to be able to handle them. One way to handle them is by factoring. Here, setting the quadratic equation equal to 0. If we can factor that, and we'll be looking at this process in a moment, then we have two products equal to 0, and therefore one of them has to be 0. It's the only way to get two things to multiply to 0 is one of them must be 0, or both. And so we can alternatively say, well, then maybe the first factor is 0, x minus 2 is 0, or maybe the second factor is 0, x minus 15 is equal to 0. And that gives us two solutions. And both solutions will work in that equation. If you try 2 or 15 into the original equation, x squared minus 17x plus 30, you will get 0. Both are, in fact, legitimate solutions. I should mention here, and I'll mention a number of times as we go through these slides, I have not mentioned the most useful, most used algorithm of all, right, in solving equations. Okay, so finally, let me close that gap. Right here, we have x minus 2 is equal to 0. And all of a sudden I say, well, that gives us x is equal to 2, right? The way you do that when you're teaching the process, as we did last week, is we add a 2 to both sides. And the minus 2 goes away on the left side, and it appears 0 plus 2 on the right side. Okay. As we all know, that's in fact not what we do mentally. Okay. What we do, and hopefully everyone has kind of been reminded of this. I apologize for only bringing it up now, that what is done is we say that the minus 2 is brought to the other side. That is an algorithm. That is a recipe. Okay. What we're really doing is we're really doing a legitimate mathematical thing of adding a 2 to both sides, but the upshot of is literally the minus 2 can be moved across the equal sign, changing its sign, changing it to its opposite. And this process we'll be doing all the time. So you will not ever see me again adding things to both sides. I will use the algorithm freely, continuously. And like I say, it's probably the most used algorithm of all in solving equations. is to be moving terms back and forth across the equal sign, changing their sign, writing the opposite of that term on the other side of the equation. With the same thing with the minus 15, it comes over as a 15. Okay. More generally, in terms of uses of factoring, we could have a trinomial here, the highest term being x cubed, which is not the kind of equation that we really will find all that useful or common in nature. So looking at more and more complex polynomials, which is a big question in algebra, we're not going to go into, we don't have to go into it because we're focused on using it and studying the real world, and equations to the third degree and fourth degree and fifth degree, as interesting as they are to pure mathematicians, are not something that we're going to run across very often. But just as an example here of this expression, three terms, 5x cubed to 10x squared and a 5x, there's an x in each term. As a matter of fact, there's a 5x in each term, right? So we could factor that out. We could factor the 5x from each term, leaving x squared minus 2x plus 1. You want to check that? Just multiply the 5x back through and see if you got what you started with. But that quadratic term that's left can be factored in itself. As we'll see, it factors into x minus 1 times x minus 1, which is nothing more than x minus 1 squared. So here's a great simplification of that equation, and we can apply the same logic. Here we now have theoretically 3 terms which are multiply up to 0, and so each one of those terms can possibly be 0. 5x possibly can be 0, which gives us x is equal to 0, and x minus 1, it's just written twice, can be 0, and so x is equal to 1. And again, if you put in either term, either solution, you will get a solution to that equation. The simplest one to see is 0. If you let x be 0, all the 3 terms go away, and because they all have an x in it. But sure enough, if you put 1 in as x, you will get 0 again on that left side. Okay, so let's now go through the mechanics of this. Factoring is nothing more than the distributive law in reverse. That's why we can check it so easily by just multiplying through by the distributive law and see if we did it correctly. Okay, so here are just examples of doing that. Thinking of the distributive law in reverse, looking at that 5x plus 10 and saying, well, what is the common factor, and how could I then write the other term so when I multiply through, I get this back. This is a matter of staring at this and realizing that, yes, I am pulling out the common factor here. In the next to last one, notice again, I have an x term, an x in each term, and all the numbers are even. And so I can pull out, in fact, a 2x. And the last one is kind of cute. If you step back one step from that, you see that both of these terms have an a minus b in them. Yeah, a minus b is, an algebraic expression. It's just like a, it's just like the number 5. It is an algebraic expression, and that expression is in both terms, and it can be factored out. Okay, so I ask you to try these in the same spirit. Let me go through just multiplication, the reverse of this, and then we'll stop for questions. If we're going to be able to factor these quadratic expressions, we have to be comfortable where they come from. So let's see how to multiply these things which turn out to be factors, and then we'll be able to think in reverse. So how do we multiply x plus 2 times x plus 3? Well, following your nose, you would use the distributive law. You would multiply x times x plus 3 plus 2 times x plus 3. That would be the distributive law, multiplying through by the x plus 3. And then we have 2 little distributive problems to finish with. The x would go through, x times x plus 3, and then the 2 would go through to get 2x plus 6. And we can collect like terms if there are such, and there are. There's a 3x and a 2x. And so we get our answer, x squared plus 5x plus 6. As we all know, that's not the way we multiply these monomial expressions like this. We've been taught a wonderful algorithm. This is the mathematics behind it. This is the algorithm that we use. We look at x plus 2 and x plus 3, and we see the x terms, and we see the number terms. We see the terms, we see the terms on the extreme left of the sign and the terms on the extreme right. Notice I use the general word terms. These expressions can be much more complicated than just an unknown plus a number. Okay? These algebraic terms can be in themselves complicated terms in themselves. The algebra does not change. The rules do not change. Executing the algorithm, it can become more complex, but it is the same algorithm, just using more complex terms. But here we have the simplest term as possible. The unknown term begins each binomial, and a number term ends each binomial. So we see those as two different pieces. The algorithm says multiply the first terms, the beginning terms, x times x. Okay, that's x squared. Second part, multiply the two back terms. Here the two number terms, 2 times 3 is 6. And now the game is to find the middle term. What is the term in the middle? And the algorithm says to multiply the outsides and add them to the insides. The outsides being x and the 3, and the insides being the 2 and the x. Okay, the extremes, as they're called, and the insides. So the extremes on the outsides are the x and the 3, the insides are the 2 and the x. Those are multiplied together. And that will then give you all the products that we have up above. This algorithm of multiplying 2 times x, the insides, plus 3 times x, the outsides, that will take care of all the little pieces that are up above that the real math shows us that we must use. The algorithm covers us if we can follow those steps, that recipe. And finally, if it is possible, sometimes it is, sometimes it isn't, for simple monomials like this, it always will be possible to combine like terms, and sure enough, we got our answer. So this is the great algorithm of multiplying monomials. This is important because it is surprising how often these kinds of expressions show up in algebraic work, both in pure math and in studying applied math. So let's give it a try. Okay, multiplying two monomials, we have the first terms, the two y terms, and the two number terms. The algorithm says do the first terms, multiply the two back terms, minus times a minus is a plus, and then to handle the middle term is the insides, minus 3 times y, and the outsides, minus 4 times y. And they can be combined to minus 7y. So if we're comfortable with this, then we'll be able to factor, we'll be able to think backwards. We'll be able to look at this algorithm literally backwards. And that's the secret of factoring. Notice this is an interesting term. You get a 3x and a minus 3x, which is 0. And this is an important example. Here we have the difference of two squares. X is squared, and 9 is a squared. And when you want to factor the difference of two squares, you will get this very symmetric result of the two squares added together as the monomials, the positive and the negative squares. We'll see these examples as we look into factoring. Here's the general algorithm. Here's what it looks like, right? We have the x squares and we have the number term, the AB. And the middle term is the insides AB and the outsides BX. And in fact, you can factor, AB plus, I'm sorry, AX plus BX. You can factor out the X, and sure enough, we have that sum term. And that's it. That is the example to look at to think about how to go backwards by saying, oh, I see what I need here. If I want to get X plus A times X plus B, if I want to factor this into these two terms, I need to find the factors of the last term, the AB, which is two factors that add up to the multiply up to the number AB. A and B will do that. And I need to find those proper factors which will add to my middle term. So this actually is the generic one for factoring of these binomials that we've been looking at. But here's it in all its glory. okay? In all its glory, again, we would multiply the front terms, A and C, the back terms, B and D, and continue to apply the algorithm, the insides, BC, and the outsides, AD, okay? There are no like terms here. There's nothing to combine. And so that is the simplest algebraic answer that we can give for just these pure letters. Okay, so trying a few examples. So before I go into factoring, I'd like to know if there are any questions so far about this.
I have a question. I wasn't fast enough. If I may, can we go back to the first slide, the very first slide you had up?
Okay, let me see if I can get out of
Sorry.
this. That's okay. The very first, this slide.
I can't write my question fast enough.
The opening slide,
Yeah.
literally the opening slide?
Sorry, I guess it was a second slide.
The second slide, that's what I would have thought. Okay.
Yeah.
Good.
So now I'm looking at the bottom where it says more generally.
Yes.
In a moment, I'm looking at it. Yes. So now I certainly see what you've done here, but I don't know how you got there. So I'm looking at the equation that starts 5x cubed, and the one that says 5x, x minus 1, x minus 1. I understand that if you multiply x minus 1 times x minus 1, you'll get x squared minus 2x plus 1, or vice versa. But I don't know how you easily went from x squared minus 2x plus 1 to x minus 1, x minus 1. How did you get?
You are asking the very question that our next slide will talk about. That's exactly what I want to go into.
Oh, sorry.
How do you do this transformation from these quadratic terms into the individual factors? That's exactly where we're going. Your question is perfect.
Yes, I'm sorry.
Okay.
Okay.
This is exactly where we're going to try.
Okay, thank you.
We first of all did in one direction. Now we want to see how we can go in the other direction.
Okay, thank you.
Let me quickly go through this. I guess I should have. Sorry, I should have jumped up. I went too fast. Okay, so yeah, so this is where we were. Okay, multiplying these monomial terms to get the quadratic terms. Now we want to go backwards, right? We want to be able to factor to go backwards. And here are just some questions in blue of having you to practice multiplying out these monomial terms. Okay, little application. John Garfield, President Garfield, when he was in the House of Representatives, actually came up with another proof of the Pythagorean theorems. This is kind of cute. We recognize the overall picture. This is the picture that we used to prove the Pythagorean theorem. He had the very clever idea of taking the picture in half. He looked at one half of the picture and saw a trapezoid. The trapezoid ABCD, okay? Trapezoid is a figure which has two parallel sides. And he saw that this trapezoid could be written in two different ways. One, you could write using the area of the trapezoid. The area of the trapezoid we know is the height times the average of the bases. And he saw three right triangles. And so you could write the area of this trapezoid as the sum of these three right triangles. If you do that, just as in the proof of the larger figure, you write the same sum in two different ways, and you can show that a squared plus b squared is equal to c squared. The reason why I show this here is because this is a nice example of multiplying out those monomials for the area of the trapezoid. So that's why that is there. Okay, now to the question that was being asked. How do you easily know to go the other way? Okay, let's again look one more time at how we go in the multiplying direction before we start looking at how we go into the factoring direction. The algorithm is we take the terms on the left, the two terms on the left, multiply them, then take the two terms on the extreme right, multiply them, And then we get the middle term by multiplying the insides 2x and the outsides 3x. And if we can, we combine like terms, which we do. And now we want to go backwards. Now, if I give you this quadratic expression, can you factor it? What you have to do, and all this is not difficult, it just takes practice. You did this a million years ago, I promise you. You have to just think of the algorithm backwards. And the algorithm is simple enough that the pieces are simple enough that this can be done pretty straightforwardly, just following the algorithm that's up above backwards. So we say, well, okay, I want to write this as two monomial terms. I see I just have an x squared to begin my term, so I know it'll be an x and an x. I don't know what the back terms will be. They're plus or minus something. They're a plus something, or they could be a minus something. So this is how we begin. This is the first step of our recipe, is to literally write this down, because we're halfway there. We've halfway found the factoring. Now we've got to find the so-called A and the B. Well, what is A and B? A and B are actually factors. They are the factors of 6. You're looking for the factors of 6, which will add algebraically to the plus 5. Look at our problem. Our problem is we have the 6 at the end, so we need the factors so that they will multiply up in our multiplication algorithm backwards. We need the factors of 6, which will add algebraically, considering the signs. You have to watch your signs to get a plus 5. And that's it. That's the backwards thought of this algorithm. It just takes some practice. Well, looking at the factors of 6, there are all the, by the way, we're dealing here with integers in our simple factoring here. Once you get away from integers, you must use the quadratic equation, which we'll do a little bit later, not today. Here, we're working with quadratic expressions with integers. So there are all the factors of 6, 1 and 6, -1 and -6, 2 and 3, and -2 and -3. Yeah, the minuses are important because we know a minus times a minus is a plus, and -2 times -3 will give you 6. They are two factors of 6. And we're looking for the combination which will give us a 5, right? A plus 5. And there it is, right? It's 2 and 3. And so there are our factors, x plus 2, x plus 3, which is where we came from. And that's it. You just need to practice this. I promise you, at one time, you were quite good at this, but you may not have thought about this in so long. Let's try another. Okay. We're looking at 15, a -15 with a middle term of 2. We set up our algorithm. We are looking for the factors of -15, which will algebraically add us up to a plus 2. What are the factors of a -15? Well, there's 1 and -15. There's the opposite, -1 and plus 15. There's a 3 and a -5 and the -3 and a 5. Notice that since we need the factors of a negative number, both sets of factors have alternating signs. They're both a minus and a plus. That's the only way we're going to get a negative product. Okay, so we're looking for the factors which will add up to a plus 2. Well, we go through them all in our minds, and the last one is the one that we want, a -3 and a plus 5. And so there's our factors. Another? Do this with me. What are we looking for? We're looking for the factors of 18. Think it through, the factors of 18, just the integer factors of 18, which will give you an 11. Come on, 2 and 9. 2 and 9's got to be it, right? We can finagle 2 and 9 to get 11. Okay, so we try all the factors, and sure enough, we go ahead and get that -11 that we're looking for with the -2 and the -9. The two negatives will give us the positive 18, and the two negatives as a sum will give us the -11. And so there are factors, -2 and -9. And the same thing always goes for factoring. If you want to make sure you did it right, just multiply out and see if you get what you came back with, what you started with. It's the same as factoring out those brackets. Okay. If I claim that x minus 2 times x minus 9 is this quadratic term, go ahead and try it. The beginning terms, that's x squared, good. The back terms, -2 times -9, that's plus 18, good. And the insides gives me a -2x, and the outsides gives me a -9x. It gives me a -9 11x. I'm good. You can always check your factoring by simply multiplying through. Here's something which comes up very often, as we'll see in our word problems, where the first term is not just x squared, but actually has an integer in front of it. And by using the algorithm, we can push this through. The algorithm doesn't change. The questions that we ask as we go through the recipe don't change. Just a little bit of mental arithmetic has to be done more carefully. Now we need 2x squared in that first initial multiplication, right? So the natural thing would be have to write down 2x and x. That will give us our 2x squared. We still want some factors. We still need the factors of -7, but now it's just a little bit more complicated because we need those factors to combine up with the 2x and the x squared to give us the plus 13, okay? So we just need to be a little bit more careful. Here are all the factors of -7, okay? They are alternating their sign. 7 is a prime number, so the factors are very few. But here, since the outside term there is a 2x, we're multiplying the 2x times the f2, right? So it's the second term, that f2 term, in the second column, that's getting multiplied by 2 in the algorithm. So now what you're mentally checking is those little sums. 1 times 2 times -7, -1 plus 2 times a 7, etc. Now we're looking at those little sums and we're looking for a plus 13. Not hard to find when you go through them all. And again, practice will really let you just move through these very, very quickly. Notice, by the way, that any one of those terms would have worked. We can now be able to factor anything. Instead of just having the plus 13, we could factor something that had a -13 term or a 5 term or a -5 term. We've got a combination now which will fit any of those middle terms. So instead of giving you a plus 13, if I gave you a -5x to factor, leaving the two extreme terms the same, I would have gone through the same, literally the same algorithm, the same set of combinations, and oh, I'm looking for a -5. It's that last combination of -7 and +1, which give me the -5. Okay. So that's it. That is how we factor. And this is a very useful skill to do. And I ask you to take a look at those. There's an application of this, very nice application, which is solving some simple quadratic equations. Let's look at quadratic equations which are already factored. And the logic here is if two things multiply up to 0, at least one of them must be 0. That is perfectly good logic. So if x -9 and x plus 7 have their product as 0, one of these must be 0. Either x -9 is 0 or x plus 7 is 0. And those are two tiny little equations which can be solved by bringing the numbers over across the other side of the equal sign and changing their sign. Okay, those equations become x equals 9 and x equals -7. And sure enough, if you put either one of those two numbers into our original equation, of course we're going to get 0. If you put 9 into the first term, 9 minus 9 is 0. Well, 0 times whatever's on the other side, it's going to give you 0. Clearly 9 is a solution to the equation, as is -7, because in the second term, -7 plus 7 will give me 0, and that will kill anything on that side to give me my equation, which is 0 equals 0. Okay, here we have a bit more complex terms. So now 2x minus 9 should be 0, or 3x plus 7 is equal to 0. This gives me a chance to use that our new algorithm here of what do I do mentally is I bring the 9 to the other side, making it a +9, and I divide by 2. Right? This needs to be done mentally, guys. If you do a million of these, as I have done in my life, but if you just do dozens of these, you will solve these mentally. So it's actually quite surprising how complex an equation can be that you can do mentally, because the algorithms are so efficient. They're so wonderful to use. And again, 3x plus 7, the 7 comes to the other side as a -7, dividing by 3. And both those numbers will work in solving that equation. Here's just a little change here. We have a simple factor of 2x times the more complex kind of factor. And so the 2x has to be 0, or the 3x plus 7 has to be 0. And now we really want to factor, okay? The idea to solve this equation is to factor it. So let's take a look. We got x squared plus 3x plus 2. We need the factors of 2, which will give me a -3. And just, 2 and 1, of course, which are the only factors of 2. Certainly from a 2 and a 1, we should be able to finagle out a 3. And yes, indeed, we can. A -2 and a -1 will give us the +2, and of course, give us the -3. So that is the proper factoring of x squared minus 3x plus 2, because if I multiply those two monomials together, I will indeed get, using my algorithm, x squared minus 3x plus 2. That is a correct factoring. And now x minus 2 could be 0, or x minus 1 could be 0. Here, I could be very stubborn and continue to make it into a quadratic equation like this and factor. This factor is something that we'll see often, the difference of two squares. X is squared and 25 is a squared. And they factor very prettily into x minus 5, x plus 5. Sure enough, if you multiply that up, you will get a 0 middle term. You've got the minus 5x on the inside and the plus 5x on the outside. They will cancel out. And so we have the two factors, and we see that the answers are just as symmetric. The answers are either 5 or -5. Yes, that is what the brackets will give us. And notice you will get the same result if you just took the square root of both sides. The square root of x squared is x, and the square root of 25 is either 5 or -5, okay? When you're dealing with quadratic equations, you must respect the fact that when you take a square root, it's either plus or minus that answer. This is how we generate the two answers. And here's also the difference of two squares. Yeah, 4x squared is a perfect square, and the factoring is the same. The algorithm does not change. We get a 2x, and a 2x will give us that perfect square. And here we get, in using our little algorithm, the 5 goes to the other side, dividing by 2. And notice we would get the same result if we went ahead and isolated the x squared. Can we do that mentally? I think so. Bring the 25 to the other side and divide by 4. X is equal to 25 over 4. The square root of that is a plus or minus 5 over 2, which is what we got the long way. Sometimes the expressions are not in a form which is all ready to factor, so we got to do a little bit of nagling. Not so hard here, just to bring the 15 to the other side, becomes a negative, and then we can factor. And here's that trinomial again. We want to recognize that this is, first of all, not a quadratic. We cannot use our algorithm on this. Okay, the algorithm does not apply to this expression. The algorithm only applies to expressions which begin with an x squared term. But we can factor out the common x and be left with an x squared term, and that we should recognize right away as a beautiful difference of two squares. Right? Yes, one of course is a square, and we get that pretty factoring of x minus 1, x plus 1. And notice now that we get 3 separate solutions. There are 3 things multiplied up to equal 0. So therefore, x could be 0, or x minus 1 could be 0, or x plus 1 is equal to 0. We get 3 separate numbers, 0, 1, and -1. And if you put any one of those 3 numbers into our original equation, you will get 0. And here I've scrambled things a little bit more. If we want to go ahead and try to factor this, we have to get it together, bring everything over to the right, to the left-hand side. The minus 7y comes over as a plus 7y. The minus 3 comes over as a minus 3, and we're left with a 0 on the other side. And this is factorable. Okay, if you just stare at that, we're looking at the factors of 3 with that 2 there, going to give us a 7. 2,
Peter?
3, 7, yeah, 2, 3, and 1, yeah, 6 and 1, yeah. Let me try to work that side of the street.
Peter?
Okay. Yes.
I have a question myself. Where there were 3 answers above, is that
Yes.
because it's a exponent of 3? Will there always
Very,
be 3?
very nice observation, Jenny. That's exactly correct. What we would prove if we went on more in our pure algebra, that expressions which have only a quadratic term have generally 2 solutions. An equation which has the highest is 3 would have 3 solutions. An equation which has the highest power of 7 will have potentially 7 different solutions. This is something that is shown as we go further and further into the theory of equations. And it is important for us to realize that when we're working with a quadratic, we need to expect that we're going to get 2 different solutions. We should anticipate that. Sometimes they're the same solution. Sometimes solution is 5 and 5. That can happen, but generally you'll get 2 solutions. Good observation. And I ask you to try those. Okay, some word problems that are generated from quadratics. Yeah, we're going to use equations, guys, that come up with products, and products will give us the x squared term. It's just a trick. It's a nasty teacher trick to turn word problems into quadratic equations by using the individual relationships that we're going to generate to solve will have products in them, and that's where the x squared terms will come up. Let's see. And the product of 2 consecutive integers. There you go. There's my secret exposed right away. The product of 2 consecutive integers is 156. Well, let n be the first integer. They're consecutive, so n plus 1 is the second integer, and you multiply them up to get 156. Okay. So here we want to solve this equation for n. The thing is to multiply through by the n and bring the 156 to the other side, and we have a quadratic expression to factor. The factors of 156, yeah, you got to think about them, and but you only need a 1 in the middle. So the factors have got to be separated by 1. We need to get a 1 there in the middle term. So 13 and 12 will do the trick. And by the way, the 2 solutions, a negative 13 and a plus 12, they will both work. Okay, what is the next consecutive integer after negative 13? Negative 12. That's the next integer after negative 13. And the next integer after 12, of course, is 13. So both will work. Both will solve that word problem, as you can show. The hypotenuse of a right triangle is 13, using the Pythagorean theorem. Squares all over the place, right? The hypotenuse of a right triangle is 13, and one side is 7 longer than the other. Find the 2 sides. Okay. Well, let x be the smaller side, therefore a plus 7 is the longer side, and there's the Pythagorean theorem. The first side plus squared plus the second side squared is equal to the hypotenuse squared. Just a sneaky way to get all those squares in there. We clear out the 8 plus 7 squared. Yeah, this is where we just have to be able to use our algorithms. I realize I'm moving very quickly through this. This is why I've given you so many practice problems, to try to internalize this, to what I'm hoping is re-internalize this of long ago. So yes, a plus 7 squared is a squared plus 14a plus 49. And you collect like terms, bring the 169 over to the other side to get the negative 120, combining with the 49 that's over there. Notice that all those numbers, all those terms have a 2 in them. Let's go ahead and factor that 2 out. 2 is certainly not equal to 0. So it's the rest that's left equal to 0, a squared plus 7a minus 60. And that's pretty easily factorable. Again, 60, factors of 60, come on, 5 times 12 is 60. We can get a 12 out of 5 times We can get a 7 out of 5 times 12. There must be a way, right? And so here we get the two solutions of -12 and 5. Although they will both solve the equation mathematically, the -12 makes no sense because of the geometry of the problem. You can't have a negative length to a triangle. So it is a mathematical solution, but it is a pure math solution, but not an applied math solution. So we rejected that solution as being invalid, and we're just left with the side of A. What a funny coincidence. The other side is 12. Isn't that something? My goodness, that must be some kind of a coincidence. The very number that we threw away because it was -12 turns out to be the other side anyway. The area of a rectangle is 24 square centimeters. The length is 2 longer than the width. Find the dimensions. Yeah, well, the area formula is a product formula, right? So if we call W the width, then W plus 2 must be the length, and their product equals 24. Okay, another sneaky way to get a quadratic equation out of this. Notice we've got to bring the 24 to the other side so that we can factor the whole mess. Easy factors of 24 to give 2. And again, we would reject the -6 as a solution because these are lengths and widths of rectangles. So only the width of 4, and again, the length of +6 is the length. The base of a triangle is 6 less than twice the height. Blah, blah, blah. The base of a triangle is 6 less than twice the height. Don't be afraid to read these word problems 2 times, 3 times, 4 times until, and write down the variables so that when you have now variables in your mind, you can read the problem again in words and you can put in your variables. I know what they're talking about. They're talking about my X or my A to try to tease out what this crazy sentence is saying. The base of a triangle is 6 less than twice the height, and the area is 54 square meters. Find the base and the height. Well, if B is the base and H is the height, here I chose to make 2 separate equations because the base is 6 less than twice the height. I wanted to try to focus on that. So the base is 6 less than 2 times H. And we know that the area of a triangle is always the base times the height over 2, always 1/2 the base times the height. So we have a nice little substitution problem. We have 54 is equal to BH over 2, but I can write for B 2H minus 6. And notice I have just an equation in H's. 54 is equal to an expression with just H's. I can go ahead and solve that equation for H. Well, there's a bit of work to do. First of all, I got a fraction I want to deal with, right? I've got that second expression is over 2. So let me multiply through by the common denominator, which is 2. And that 54 will turn into 108. And I'll just be left with 2H minus 6 times H. Let me multiply that through and get 2H squared minus 6H is equal to that 2 times 54. And then I bring everything over to the other side. And again, notice that everything is even. I can factor out the 2. A lot easier to factor that expression. H squared minus 3H minus 54 is equal to 0. Factoring that, going through the factors of 54, we come up with minus 6 and a 9. Since we're dealing with a geometric figure, we reject the minus 6 and take the 9. But here, because of the complexity of the relationships, here the other number is not 6, but in fact it's 12. Okay, the height turns out to be a legitimate height is 9, and the base is 12. And sure enough, if you multiply up those and divide by 2, you will get 54. Okay, and here's a bunch to try. Questions?
Yes, Peter, I do. That first one on the homework.
Oh, I would like to see if we can finish and go through these questions afterwards. I'd like to try to finish the presentation and then go back to all of these problems.
Yep, okay.
Okay. All right, second topic. Last topic, I promise this is the last torture of looking at purely algebraic mechanics and artificial problems to use them. Okay, next week we will stop with the artificial problems. We're going to study Archimedes' law of buoyancy, okay, and draw out some beautiful and interesting relationships. This artificial mathematics will stop and we'll start to investigate the world, but using these techniques, right? That's where we're trying to go. We're trying to do these exercises just as you do in practicing your instrument, just as you're practicing playing soccer or tennis. You do these mechanical little pieces over and over again so that when the game is, or when the concert is, when you're playing the piece, this stuff becomes easy and automatic. It's not stuff that's in the way, but these are useful tools in thinking about the real problem. That's what we're trying to do, guys. Okay? I know you know that, but as a teacher, I just need to explain myself one more time. Okay, adding fractions. This is easy because we already have the common denominator, right? They're both over 2x, so we simply can combine that. A 3 and a -7 is a -4. But we can simplify that. -4 over 2x. We can pull a 2 out of each and get -2 over x. Here we don't have a common denominator. And here's the mathematical way to add up some two fractions which don't have a common denominator. You make the two expressions into two fractions which have a common denominator. You do that by multiplying by ones, by very clever ones. X over 5 multiplied by x over x, which is just 1, will become an expression over 5x. And 1 over x multiplied by 5 over 5 will become an expression that is over 5x. And now that we have two fractions both over 5x, now we can go ahead and add the numerators and get x squared minus 5 over 5x. Okay. We know this is not the way we add fractions. In fact, we use an algorithm. So let's do it again. What we look at is we look at our fractions and we find the common denominator. Common denominator here is 5x. And now we have our algorithm. The algorithm, as we know, is 5 into 5x goes x. X times x is x squared. X into 5x goes 5. 5 times the 1 is 5. Right? And that's what I've done. That's the algorithm. Okay. You have to be able to mentally divide these individual factors into the common denominator. But gosh, the common denominator is, you picked it so that the 5 and the x were factors. That's why you picked it, so that the division would be so easy. So mentally, you should be able to do this easily because of the common denominator that you picked. Okay, we'll try this one. Common denominator is x times x plus 3. Nothing you can do about it, just they're just a product together. But that makes the algorithm very easy, right? Because x into x times x plus 3 is the x plus 3. And x plus 3 into x times x plus 3 is just the x. Right? And so multiplying those by the appropriate numerators, we get 1 times x plus 3, and we get 2 times x. And clear away, combine like terms, and get this. And I know you want to cancel those 3's somewhere or other. You can just taste it. There's got to be a way that some of those 3's have to go away, but there isn't, guys. There is no way to cancel those 3's. You cannot find a factor on top and bottom. Yeah, you could factor out the 3. That's a perfectly good thing to do. 3x plus 3, you can factor out the 3, but look down the bottom. There is no factor of 3 down the bottom. At x plus 3 is not a factor of 3. It's not 3x, it's x plus 3. You could go ahead and multiply the two factors up together. And, which really you should do, and this would be the proper way, the polite way to write the final algebraic expression. You would not really leave it as x times x plus 3. You'd write it as x squared plus 3x. Got to be polite here. And again, you got 3's all over the place. But an x squared term does not have any kind of a factor of 3, and there's nothing to cancel, as much as you would like. I'm trying to point out a very common, so-called silly mistake. People trying to slash out things that they see. You cannot do it. What you're really looking for is ones. You're looking for ones. That's what you can slash out. If you can't find a 1 mathematically, then there's nothing to be simplified. Okay, we want to add up these two fractions. Fractions? Yeah, 3y squared is a fraction. Any algebraic expression is over 1. And voila, it is a fraction. And now we have a common denominator of 5y, and we do our sing-song algorithm. And notice that 1 goes into 5y times, and so 5y times 2y squared is 15y cubed, and 5y goes into 5y 1 time, and 1 times 2 is 2. Okay. All right, so I ask you to try those additions of fractions. And now our last topic is to deal with equations with fractions. First issue I want to address is, when can you cross multiply? Some people like to cross multiply anything which is not nailed down. There is only one case in which you can use the algorithm, very useful, very handy, very quick algorithm of cross multiplying. The only time you can cross multiply is when you have an equation of the form A over B is equal to C over D, where A, B, C, and D can be very complex expressions in themselves, but there's no plus signs to be found or minus signs to be found. It's just one term, one algebraic term over another algebraic term is equal to a similar kind of situation. Then you can cross multiply. Let's see an example. 3x is equal to 3 over x is equal to 4 over x. I'm sorry, x over 4. We can cross multiply, right? We can multiply the 4 times the 3 is equal to the x times the x, right? I'm multiplying across. So I get 12 is equal to x squared, and I can go ahead and take the square root of both sides. There's nothing magical about cross multiplying. It's an algorithm. All that I'm doing is multiplying by the common denominator. That's all that I'm doing. I'm multiplying the equation through by 4x, which is the common denominator. And 4x times 3 over x is 12, and 4x times x over 4 is x squared. I get exactly the same equation. It's just when you have the opportunity to cross multiply, it is quicker mentally to do that than to be multiplying by the common denominator, doing all these canceling your head as you go. Cross multiplying gives you the ability to just multiply up the terms and then start canceling things out on both sides as you go. It makes that initial multiplication easier. That's why it's used. That's the only reason why it's used. It is nothing magical about it at all. You can always multiply through by the common denominator. You don't have to know a thing about cross multiplication. Your algebraic life will go on just fine. The problem is when you try to cross multiply when you shouldn't. And that's why I'm trying to warn you against it. Okay, here's an example, perfectly good example. We can cross multiply. The x gets multiplied by the x minus 1. I've done it mentally. Multiply the x through, x squared minus x, and the 5 times the 4 gives me 20. Oh, son of a gun, don't I have a quadratic expression? What a sneak. So I factor and get my two solutions. Here is everything in all of its glory. Okay, I have two sets of that a's and b's. X plus 2 can be thought of as a, and y minus 3 can be thought of as b. These are products, these are terms over each other, and I can in fact cross multiply. And it is easier to do this. You can multiply the 5 plus the y plus 5 times the y plus 2. You kind of just write it right up there and take the bottom there, the y minus 3, and bring it up on the other side. It is easier as a recipe to do this visually and to write it down as opposed to multiplying by that big mess of y plus 3 times y plus 5. Y minus 3 times y plus 5. It is a very nice algorithm. And now we want to be able to multiply up monomials. That's why we did that. Notice there's a y squared on both sides. They'll go away. And the minus 7y will come over to the other to the other 7y to give us 14y. The 10 will go over as a minus 10 to give us 2, and that will give us y is equal to 1, 7. Yeah, it looked like a quadratic equation, but it's not because the y squares in fact canceled out. And we only wound up with a linear equation. Here's another one. Oh, I'm sorry. There's the one I want you to try. There's the one in blue. Okay, that I want you to try. All right. Let's look at some a bit more interesting and see if we can't do this quickly. Fractional equations here, we want to multiply through with a common denominator. Common denominator here clearly is y. And multiplying through, you get a 3, you get a -4, and you get a y on the other side. Well, 3 minus 4 is -1, and there's our solution. Okay. By the way, 3 over y minus 4 over y, those are already over. They're already over a common denominator. I could immediately have said that's 3 minus 4 over y, which is -1 over y, which will give us y is equal to -1. Right? We know that there are many, many different kinds of algebraic manipulations that will give you the answer. Some are quicker than others, some are cleverer than others, some are more elegant than others, but they all work. And it's just a matter of experience of what occurs to you. But it's nice to sometimes see alternate ways. Okay, common denominator here looks like 6x to me. I've got x, 2, and 6. Looks like a 6x is the common denominator here. Multiplying through carefully, 6 minus 3x equals a minus x. Yeah, because 6x times minus 1/6, the 6's cancel, and I'm just left with a minus x. Okay? A simple equation to solve. Here, looking at the denominators, it looks like 4y. Looks like the common denominator to me. Multiplying through carefully. Here, looks like 2x would be the common denominator. Multiplying through carefully. Oh, son of a gun, a quadratic equation. Okay, an easy one to factor, getting 2 separate solutions, -2 and -3. And if you put those in, both numbers in, either number in, that they are the solutions to that equation. Here's where we talk about different ways of doing things. It occurs to me that I've got 2 numbers there, one on each side of the equation. Why don't I just get the number out of there, just bring it to the other side, bring 3 halves to the other side and make that a 7 halves. After all, 2 is 4 halves. So now I've got, oh, look at that. I've got a situation where I can cross multiply. By getting rid of the -3 halves, by making it into its own simple fraction on the other side, I now have fractions over fractions, which I can cross multiply. And you've got to admit that is an easier way to go. It's the 2 times the 3 minus x and the 7 times the x minus 1. However, if you wanted to be stubborn and look at this thing, same equation, right? Not a new equation. Look at your denominators. The denominators seem to be 2 and x minus 1. If you went ahead and multiplied 2 times x minus 1 by all those terms, the 2 survives the first fraction, the x minus 1 survives the second fraction, and and the x minus 1 survives the second term. And you only are left with the x minus 1 times the 2 on the other side of the equation. So if you do that carefully, clear everything out, you will again get a 5. Okay. Final word problems. Word problems which I'm artificially generating fractions. How am I going to do this? A lot of things, they're going to be number problems about inverses. They're very pretty. They're very interesting problems. Properties of inverses. It's nice. The inverse of 2 more than a number is twice the inverse of a number. It's interesting if you read that once you have x as the number. You can read it as the inverse of 2 more than x is twice the inverse of x. You're getting there. Another read, but you are getting there. It doesn't come in the first read, I promise you. So if x is the number, then 2 more, then the inverse of 2 more than the number, 2 more than the number is x plus 2. The inverse is 1 over that. is twice the inverse of the number. If the number is x, then the inverse is 1 over x. By the way, the other name for the inverse is the reciprocal. And I will use those interchangeably. I think I more favor inverses than reciprocals, but I will use the word reciprocal as well. So there's our equation. I simply just took that 2 times 1 over x and wrote it as 2x. You want to do that right away. You want to get your algebra as simple as possible before you start fooling around with solving equations. You don't leave a mess like 2 times 1 over x if you can help it. So notice we have a common denominator of x times x plus 2, and we can do that, or you can just simply cross multiply and get the same result. And x is equal to -4, just to do a check. Okay, the inverse of 2 more than the number, or 2 more than -4 is a -2, and 1 over -2 is indeed 2 times -1/4. That is the correct solution. It does solve the relationship. The sum of the inverses of 2 consecutive odd integers equals 0. That's interesting. The sum of the inverses of 2 consecutive odd integers equals 0. What could those 2 consecutive integers be to add up to 0? Well, let x be the first odd integer, so x plus 2 is the next one. And there are the 2 inverses that I'm adding up. 1 over x plus 1 over x plus 2. I'm told that that's equal to 0. The common denominator is x times x plus 2. And multiplying through by the common denominator, I will get x plus 2 times 1, which is x plus 2. I will get x times 1, which is x. And that clearly is equal to 2x minus 2. And my number is -1. The number I'm looking for is -1, and the next odd number is 1. And certainly the sum of those 2 inverses do add up to 0. Okay, so we have those to try. And finally, the last set, some motion problems. John walks 2 miles and Mary walks 3 miles at the same speed. Mary takes 15 minutes longer. How long does John walk and at what speed? Let t be the time John walks. By the way, this is something you can always try in a word problem. Look at see what you're looking for. What is the problem looking for? And just give that thing a name. Give it a variable name, the power of a name. By calling what you're looking for, the time in which John walks t, and then go back and look at the problem again with that, substituting in your mind t, the algebra begins to develop in your mind. It's the power of the name, the variable name t, can do wonders. Because if t is the time that John walks, then Mary's time is t plus 15. All of a sudden, Mary walks 15 minutes longer, becomes the algebraic expression t plus 15. The mysteries begin to, fall away. And v is the common speed. We do have 2 unknowns here. We have time and we have speed. But distance is always equal to speed times time. And so we're told that the distance 2 is equal to vt, and Mary's distance 3 is equal to v times her t. And there are 2 equations and 2 unknowns. In the spirit of showing many, many ways of solving this, ways which I would like you to think about, first way is just to do the old substitution. This is grinding it out, okay? We take the first equation, 2 is equal to v over t of vt, and I solve for v and stick it into the second equation, right? This is a classic substitution. I have a fractional expression there, 2 over t, and multiplied by the common denominator t. I get 3t on one side and 2 times 2 plus 15 on the other, which I just distributed right through. A simple equation to solve. I get t is equal to 30, and so Mary walks 15 minutes longer than that, of 45 minutes. And what's the speed? Well, the speed is t over 2. That's how I began. So if the speed is t over 2, then 2 over 30 is 1/15 of a mile per minute, better known as a mile every 15 minutes. Okay, and you can check that on Mary's side. Mary's distance will be 1/15 of a mile per minute times for 45 minutes. But if you look up from your nose and stop grinding for a second, notice that VT is equal to 2. Okay. The algebraic expression VT is equal to 2. Now look at the second equation. 3 is equal to V times T plus 15. Isn't that VT plus 15V? Okay, when you multiply the V through, but VT is 2. So 3 is equal to 2 plus 15V. And so 15V is equal to 1. And sure enough, V is equal to 1/15 as we showed. And the rest of it just follows. Or we can take the two expressions, write them down under each other, and you say, look at that. I've got these two products here, and I've got a V on both top and bottom. Suppose I would divide one equation by the other. Oh yeah, you can do that because the VT and the 2 are the same, and the V times T plus 15 is the same as 3. That's what the equal sign means. So I can certainly say that those two fractions are the same. But look what I get. The V's cancel out, and I have a very nice cross-multiply equation just in T, okay, which will give me the 30. Or I can be really clever and write them in the opposite way, okay? Put the T plus 15 up on top. So not only will the V's go away, okay, but I've got T plus 15 over T. Oh, I can simplify that even one more. That's 1 plus 15 over T. Yes, the T on the bottom is over both terms. That's why it's in a bracket. So it's T over T plus 15 over T. But the 1 on the other side, yes, throwing in the 1 on the other side, 15T is equal to half. A simple cross multiply gives us that 30 minutes as well. So I like it just to look at these and say, yeah, there's all kinds of ways of solving algebraic equations. This business of putting one fraction dividing by another is a very nice trick that you can use very often when you have these kinds of simple multiple equations like this. And here I've done it here with this problem here. It's exactly the same, guys. This is exactly the same as the previous slide. Exactly. The expressions are different. The algebra is the same, identical. It's the numbers and the letters. Here the problem is instead of the time being the same, instead of the velocities being the same, the times are the same, and the times get canceled out. And there, in fact, I did the full solution there using that last method of getting the answers. Okay, so that is that. I don't know how much time you guys had to look at the problems I left you with, but with a little bit of time we have left, what kind of questions can we answer?
I had a problem with slide 11.
Slide 11, here we go. All righty, try these. Which one?
The very first one.
Okay, two consecutive odd integers have a product of 63. I claim that the answer is a -9 and a -7. Those are indeed two consecutive odd integers. That's true about them. And they do multiply up to a positive 63. So
I
that
guess
is, so that
can you
is
get
the
us
right
started
answer.
on it?
So let's take a look at my solution and see if, try
Oh,
these.
I didn't know the solutions were down there, darn it.
Oh yeah, you gotta, oh gosh, guys, you gotta read my emails for one thing. It helps to read my email. It really does. I'm trying to communicate.
I know.
And
So many.
yeah, you have to kind of look at the whole thing. I thought, as I said in the email, it might be helpful if I sent you the answers right away for you to compare.
I thought
Anyway,
that was last week.
Yeah, so there we go. So there is the solution of, again, it's a product situation. If one number is X, the next one is X plus 2, and you get a quadratic. And when you factor the quadratic, you in fact get two solutions, the 7 and the -9. And so both work, both 7 and 9 and -9 and -7 both work. Next question.
Huh. Who did that?
I'd like to look at the second one. The second one is a nice substitution if I can, guys. Let's look at the next one. In a right triangle, the longer leg is 2 less than the hypotenuse. And the shorter leg is 1/2 of 1 more than the longer leg. See, I'm being very diabolical here. I'm not giving you two relationships with the hypotenuse. No, I'm not doing that. I'm telling you one leg is related to the hypotenuse, and the second leg is related to the first leg. So I'm forcing you to do a substitution, okay? This is pretty much, the algebra in all its glory for these kind of problems. In a right triangle, the longer leg is 2 less than the hypotenuse, and the shorter leg is 1/2 of 1 more than the longer leg. Use the Pythagorean theorem to find all 3 sides. Okay. Well, let B be the longer leg, let A be the shorter leg, and C be the hypotenuse. Now, if you go back and read that gobbledygook sentence, it will make a lot more sense if you put in your mind A, B, and C, because we know that A squared plus B squared is equal to C squared. That's one of our relationships. We do have 3 unknowns after all. We need 3 relationships. The other 2 relationships are up above, and they can be teased out if you think about A and B. So the longer leg, B, is 2 less than the hypotenuse. B is equal to C minus 2. The shorter leg is 1/2 of 1 more than the longer leg. It's 1/2 of 1 more than the longer leg. A is half of B plus 1. So notice I gave you B in terms of C and gave you A in terms of B. And now what are we going to do with the Pythagorean theorem? I need to get the equation in just 1 letter. Any letter will do, but I need 1 letter to solve this thing. So if you look and see that I have A in terms of B, it's pretty easy to get a C in terms of B by just solving the little B is equal to C minus 2. If B is equal to C minus 2, then C is equal to B plus 2. And now C can be written as in little b. C can be written in little b. A I was able to write down in terms of little b, and now I can stick all that into the Pythagorean theorem. A squared, which is B plus 1 over 2 plus B squared, is equal to C squared, which is B plus 2. And it's a big mess. You got to square all this stuff, clear everything out, factor. It's just a big algebraic mess. The problem is here in the substitution. How to take the Pythagorean theorem, which is in 3 variables, A, B, and C, 3 unknowns, and use the information up on top to write that in 1 unknown. And one, I think the one most obvious to use is that B term, because C and B are given and A and B are given. And so let's write everything in terms of B. Okay, so there's where we are. My question before you go is, what should we do? Should we continue on with the lecture that I prepared on Thursday? Should we schedule it for some people who would like another class to go over this lecture and the previous stuff before next Thursday? Or I'm so bewildered here, I don't know what to say. I guess those are the 3 places where we're at. Could you send me an email just responding? The easiest is to respond to my previous email. It's reply button and just say something. Tell me what you'd like to do. Would you like to have an extra class going through this? I would like to not, if I don't have to, sacrifice the last 5 classes that we have in what I want to try to do by reviewing this stuff. But that may be the best thing to do, is to actually just use next class, the 4th class, to continue reviewing these kinds of mechanics. So maybe that's a 4th choice of what you'd like. Give me a response. Tell me what it is that you'd like to do. I'll collect all those. I'll email you guys back maybe by the weekend, we can make a decision as to what is the best way to proceed. I hate to be belaboring this, but I'm just trying as best I can to keep everyone on the same page so that we can enjoy the rest of the course without me totally bewildering and snowing you with equations and manipulations which you just are not following. That's my goal, right? That's what I'm trying to do. All right, so let me sign off with that.
Can I interrupt one more time on that problem?
Yes, please, please.
Well, to be an odd integer, doesn't it have to be the 2n plus 1 that we went over in the first class or the second class?
You could do it that way. That's a fancy way, but it's actually not necessary.
Well,
Just
I got a different answer for that.
You did. Well, that's
Yeah.
good. I will try that.
Maybe you try it and tell me if where
So you tried 2n plus 1 and 2n plus 3.
Yeah.
You did.
Actually, my answers don't add up to 63. So that, I mean, they don't multiply to
Okay,
63.
that's definitely a problem.
But it's,
Okay.
but if you just do x and x plus 2, x could be even, right?
It could, but because of the nature of the problem, as you see, the algebra actually is smarter than we are and gives you odd numbers.
Okay.
Yeah.
All right.
All right,
Thank
guys.
you.
I'm gonna stop the recording and please see if you can. Where am I here? What happened? Trying to stop the recording.
You stopped your
Yes.
PowerPoint.
Okay, I will stop the recording now.